the lecture, and then we're going to make it available online. All right. So I don't know if you had time to check the part of the lecture that I uploaded this morning. Did you guys check it?
Yeah.
Okay, so Eva saw it. Did you guys, Christoph and Martin, did you have time to see it?
Yes.
Okay, good. So where we stopped at why is HTTP is not suitable for IoT applications, and you can see the screen, right? You can see the presentation. Just checking.
Yeah.
All right. So mainly, it was not very well suited for IoT because it did not support many-to-many information exchange or multicast. It was not built to support event-based transmission. So mainly HTTP was based on the request response paradigm, and it was designed for that. So if you want to design it or redesign it or reprogram it to work with event-based transmission, then you get a headache of establishing connections every time you want to send a request, which is not very robust. Also, IoT is usually very sensitive to power consumption because of that these devices are battery powered, and it needs the responsiveness of sometimes of near real-time delivery of information. And both of these things are not really strong in HTTP because one of the things is that it runs on TCP, which requires that the connection stays open the whole time, and this consumes a lot of the battery resources on these devices. Right, and here you can have a look at one case study that was done by Google where they tested HTTP and MQTT, where actually both of them run on TCP. And the funny thing is that, as I mentioned before, is that for one node, so for one transmission, HTTP is much better. But once you add or aggregate more sources, then you start to see the importance of having a different approach. All right, so now we will move on to two suitable protocols for IoT. Each one of them has its own advantages and disadvantages. And let me see why this is not moving. No, okay. So the first one is Constrained Application Protocol, or CoAp, known as CoAp. The Constrained Application Protocol is a specialized WIP transfer protocol. So it's similar to HTTP in the sense that it's also a WIP transfer protocol. However, it was designed to be used with constrained nodes and constrained networks for the Internet of Things, or more specifically in machine-to-machine communications. So it was mainly used for devices that don't have the same capabilities, but require maybe less of a quality of service than HTTP. So the similarities between HTTP and CoAp is that servers would make the resources available under a specific universal resources locator, and then clients would be able to, unique resources locator, and the clients will be able to access these resources using specific methods. So similar to if you want to get or put or post or delete. Also similar to HTTP, CoAp can carry different types of payloads, and it has a specific option field that specifies the type of this payload. So as we said that HTTP is a purely text, or as in the name, hypertext, all the data is transferred in pure text, and then all the metadata is included after that, which includes the formatting or the fonts or anything like that. This also holds for the data type. So the data type also gets input into this metadata field, and in CoAp it's known as options. So we'll see that later. All right, so next, the main features of CoAp are mainly that, as we said, it's a web protocol that was designed mainly for machine-to-machine communications for constrained devices. The CoAp was designed for asynchronous message exchange. So this means that when a client issues a request, the server might choose to answer now or after a specific processing delay. So this delay itself is supported in CoAp, so it does not need to be a synchronous transmission. So it does not need to be exactly after the transmission or at the same time. The overhead of CoAp is quite low, so you don't have the same overhead that you have with HTTP. And we will see why in the next slide. It has also a unique resource identifier support. So we said identifier because it can be a location as an HTTP, or it can be something else as a specific, as something specific that would identify a resource. And the last thing is that it supports proxy and caching. And proxy is a word, it's similar to forwarding. So you can give permission to an intermediate node to make a request in your name. So this is a very neat feature that that gives you the possibility to actually route your own requests or do it anonymously. Or in the case that you don't have enough range of communication to contact the server yourself, then you can actually mesh your request through multiple nodes. All right. The next thing is that we're going to look at how the CoAp is made. So mainly CoAp is made of two sublayers. First is the request response layer and the message itself. And these both layers are layered on top of UDP. UDP stands for User Datagram Protocol, and it's a protocol similar to TCP that kind of describes the communication protocol between two different nodes. And the thing about UDP is that the communication itself exists as a stream of packets that has no order, no delivery reliability, or no some kind of flow control. And this differs from TCP, which is very stringent when it comes to order. So all the packets are going in exactly the same order they were transmitted. And acknowledgements are sent also in the same order they need to be received. And this kind of gives you the security you need if you want to match a specific acknowledgement to a specific packet, right? However, in UDP, you don't have this ordering, and therefore you need to employ something else in your application layer protocol to support or to be able to order the packets if they go out of order, right? So we will see that later. But the point that I wanted to make here is that we said before that CoAp does not have the same overhead as other transmission protocols. As other application layer protocols. And that's because it runs on UDP, which is usually a low overhead communication protocol. And UDP mainly is used in applications where you don't need all the packets to be delivered reliably, but you need most of the packets to be transmitted and received with very low latency. So this is usually used for online gaming or streaming activities like voice over IP, where you don't need like a high definition voice. So you don't need all the packets to be received, but you need most of them to be received right away. All right, so this is about UDP, and back to CoAp is that the request response sublayer, it manages the interaction between the client and the server. So the client sends a request and the server would respond. However, the role of the client and the server are not actually fixed. So the terms client and server only identify who issues the request and who issues the response. Is that clear so far? Do you guys have any questions?
No questions yet.
All right. So now let's have a look at how the message itself. So here we looked at, so we know already the request response paradigm, right? We spoke about it in the last part, but let's have a look on how a message looks like in CoAp. So first of all, CoAp supports 4 message types. The first one is confirmable, and these are quite reliable messages. And as I said before, since UDP itself does not have handshaking or acknowledgements, and UDP is a lower layer than the application layer, so this is in the transport layer, so you need to have support for acknowledgements or confirmation in the application layer. So this is usually how protocol designs work. You have a specific function such as handshake or acknowledgements, and you need to decide where to put it. You can put it in the transport layer, so you can use something like TCP, and there you don't have to worry about it in the application layer. But if you decide that you want something faster for the transport, so you use UDP, then you still need to put the acknowledgements or the confirmation function in the application layer. And therefore, CoAp needs to create the support for this confirmation in the application layer. So here, the first type of message is confirmable. These are quite reliable, and the reception must be acknowledged by the server or the recipient, right? The second type is non-confirmable. These messages do not need confirmation. Acknowledgement is a type of message that is an acknowledgement to a confirmable message, or a reset, which means that I was not able to process your message. Please resend it again. Every CoAp message is composed of these 3 parts. First is a header that is these 2 parts. So you have the version, the type, token length, code, message ID, and then the token itself. And then you have an options field that specifies, usually, as we said before, the data type that you're transmitting or any other meta information that you want to transmit together with the payload that contains the actual data. Now, the version indicates the CoAp version number. So there are multiple implementations of CoAp, and usually the transmitter and the receiver, or the client and the server, should run the same version in order to be able to communicate properly. Then you have the type, and the type indicates the type of the message, as we said from the 4 types here. And it's usually 2-bit because you have 4 different possibilities. So you have either 00, 01, 10, 11. Then you have the token length specifies the length of the token put here. We're going to say the function shortly. Then you have a code, and this code is similar to the code returned by an HTTP request. So either this message is a request, then this code is usually 0 family, or it's success response, which is in the 200 family, or client error response 400, or in the server error response, which is 500. Then you have the message ID, and this actually is used to detect message duplicates. and to match the messages of type acknowledgement reset to messages of type confirmable, non-confirmable. So just to explain this a bit, what happens in UDP, since you don't have any kind of arranged packet delivery, is that you might receive one packet and then shortly after that you receive the same packet once or twice again. And this is because sometimes packets get stuck in on the way and then they get delayed. So when the transmitter doesn't get an acknowledgement, it kind of sends the packet again. And then at the end, you end up with 3 or 4 duplicates. So you need this message ID in order to remove duplicates, and also in order to match an acknowledgement to its specific message. So you don't acknowledge another message, and then you kind of have already a bad communication. Now let's come to the token. The token value is usually used to correlate requests and responses, and it has something to do with how to identify a specific client and its message. So it could have been also labeled as client message ID. So it's a combination of the message that was sent and the client that actually sent it. And it also serves as some kind of security, because this token represents the client that sent the message. And if you have a eavesdropper that is trying to send requests and he doesn't have actually, he should not have access to this specific resource, then he should not be able to generate this token and gain access to this resource. All right, so now let's have a look at some possible messages interactions between clients and servers. So here you have a client that sends a confirmable type message with a message ID, and the server is acknowledging this this message. So you have here the type of the message is a confirmable message, and here this message is an acknowledgement, right? And as you can see, the ID has to match on the acknowledgement and on the request. Or you can have the case where the client sends a confirmable message and the server is not able to process this message, so it sends a reset, which means that I was not able to process that. Please send it again, or if it's not important to you, then do nothing. Or the client just sends a non-confirmable message to the server, and therefore the server is not required to answer anyway. Now, the message sublayer determines how two communicating parties should deal with individual messages. However, the messages may carry a payload, and we said that the payload itself does not describe anything other than the payload. So it doesn't describe the data type that is inside the payload. It's just pure data. And also the payload may contain a request to specific resources or answers to previous requests. So as we said before here, that the type of the message, sorry, that it was, let me check quickly. What was it? All right, so never mind that. Here, the payload itself can be a specific request, or it can be an answer to a request. So the design of the message in CoAp, it's not that the request is different than the answer to the request is that you send your own request in the payload. So you send the address or the URL that you need to access inside the payload, right? So here you have an example. For example, the method that you're using is get, and the URL that you want to access is sensors temperature ID 42. And this is a specific URL that you want to access, right? And as we mentioned before, that the requests are identified by a specific token, and the requests must carry a method, which here is get, and a specific unique resource identifier, which is in this case the location of the identifier of the resource that you want to access. Now, the message exchange to complete a specific request response interaction, it varies between the type of messages that being exchanged. So the type here being confirmable or non-confirmable. So here we have different types of interactions, and this is actually due to the fact that this is an asynchronous protocol. And because it's an asynchronous protocol, we must also account for the fact that a server indeed can answer after a specific delay, and that the acknowledgement and the information that I need to access might not be sent in the same message. So as an example here, you send a confirmable message with a request to access the resource specified here, and you have a token specified here. And then what happens is that there are possibilities. The first possibility is that the server would answer with an acknowledgement and the data that you want to access, which is 20 degrees Celsius. And here you have the same token to match the request and the response. However, there's also the possibility that you send the same exact message, but the server will first acknowledge your request, and then it will answer with the specific information that you asked for. And here you can see that the ID of the message is different than the ID of the request and the acknowledgement. However, the token is the same. So basically, this is the difference between a message ID and a token. The message ID tells you to which request are you acknowledging, and a token tells you to which request you're sending this data. And then the client will acknowledge the receiving of this information with a message ID that is matching to the message ID he is responding to with an acknowledgement. Or there's also a possibility where you send a request with a non-confirmable message requesting a specific resource, so you don't get an acknowledgement right away. However, you get the information that you asked for, and again, it has the token of the original request, but a different message ID, because this is not an acknowledgement to the original request. All right, so this is all about CoAp. So far, do you guys have questions? Okay, good. So I'll take it that you guys don't have any questions.
Sorry, I have just only one question.
Yeah.
What is the difference between, or is the payload the code, or is there a difference?
So here.
Yes.
Yeah. So no, the code is as we said in HTTP, it's the return code. So if your request was a success, or if it was an error, or if it's actually only the request. So since this message might be a request or a response, then this code tells you, this is the part that I was looking for and I couldn't find before. This code tells you whether this is a request or a response. And in case it's a response, it also tells you the code of the response, which might be 200. So here, let's go back to this one here. So this is similar to this. Whether this is information or a success, redirection, client error, or server error, with the addition of the fact that you have 0xx, which means that that this message is a request.
Okay. And
Yeah.
how many bits does the payload have, or where?
It supports multiple payload sizes. So usually this is defined in the options. So the options also tells you the payload size. I'm not sure. Let me look quickly. So usually it's 1024 bytes for the payload size. This is usually the usual size for the payload.
Oh, okay. Okay.
So 1 megabyte. Yeah, you're welcome. All right. So I just got a notification from Zoom that the meeting is ending in 10 minutes. So maybe we stop here and rejoin again to finish, because I don't want it to cut in the middle of the remaining part. So you guys can just rejoin the same link, I guess, and then we'll start again.
Okay.
All right.
Okay.
Yeah.